This chapter 1 teaches you how to derive zero coupon rates from ordinary yield curves, as well as discount factors for each maturity using a process known as bootstrapping. We begin by considering a bond market that has only 3 securities outstanding: a 1-year, 2-year, and 3-year note with the characteristics you see here. Note, among other things, that the 1-year note is a discount security that pays no coupons and is issued at a $5, in this case, discount from its face value, or from par. The other 2 securities are issued at par but pay a coupon of 8% in the case of the 2-year and 9.5% in the case of the 3-year. Now suppose that you wish to determine what would be the yield on a 2-year zero coupon bond when none exists in this market. You could be needing to do this for any number of reasons, including as part of a pricing exercise for a new bond issue, or as part of a valuation exercise for a project or investment, or for purposes of pricing a swap or other derivative. Remembering that any bond has a price equal to the sum of its cash flows appropriately discounted, you are able to write this equation for the 2-year note. Price, 100, equals first cash flow of 8 times its discount factor plus second cash flow of coupon 8 plus principal 100 times its discount factor. We emphasize again the inclusion in the final cash flow of the par value, or the principal, of 100 in addition to the final coupon. But you know already that df1 equals 0.95, since the 1-year note represents the right to a $100 cash flow in 1 year and is priced at $95. So you can solve the above equation for df2, which now has only one remaining unknown. Rearranging the above equation gives df2 equals, rearrange terms, equals 0.8556. Furthermore, df2, being the discount factor for a cash flow occurring at the end of 2 years, must equal 1 over 1 plus z2 squared, where z2 is the 2-year zero coupon rate you are seeking. So solving the equation in front of you enables us to write what has just appeared. The above example should have made you realize that from any discount factor you can derive the corresponding zero coupon rate, and from any zero coupon rate you can derive the corresponding discount factor. In general, we can write dfn is 1 over 1 plus zn to the power n, where zn means the zero coupon rate for a tenor of n years, an equation we will be using shortly. One last thing to note before we proceed is that the note we are decomposing does not need to be trading at par. If, for example, the 2-year note is trading right now at 98, suggesting, of course, a higher yield to maturity than its coupon, we would simply replace the 100 in the above equation with 98 and proceed exactly as before. The second 100, which appears in the final cash flows numerator, always remains 100, of course, since this refers to the face value of the note. Now, suppose you also need to derive the 3-year zero coupon rate and by extension the 3-year discount factor. Proceeding as before, you write the fundamental pricing equation for the 3-year note as price 100 equals, as always, each of the cash flows multiplied by its respective discount factor. And you remember to include in the last cash flow not just the coupon of 9.5 but also the principal, which enables you to solve for df3 since you already know df1 and df2. This leads to df3 equals, we've simply rearranged the terms of the above equation, so df3 equals 0.7566 appearing on the right of the rectangle. And since, by definition, df3 equals 1 over 1 plus z3 to the power 3, it follows that z3 equals 9.7435%. More generally, assuming we have already calculated df1, df2, etc. all the way to dfn minus 1, and that we now wish to calculate dfn from the regular coupon-bearing note maturing in n years and carrying an annual coupon of Cn. We would write for this note, again, that its price equals its cash flows, with each cash flow being multiplied by its own appropriate discount factor, which enables us to solve for dfn and therefore for zn, the zero coupon rate for n years, since we can observe the price of this bond, price n, as well as its coupon, coupon n, and since we already know all the df's in this equation up to but excluding the last one, which is the one that we are seeking. Rearranging this equation enables us to write the following, and upon one further rearrangement we get dfn equals essentially the price of that bond minus the coupon of the bond multiplied by the sum of all the previous discount factors that we know already, not counting obviously the one we are seeking, and then dividing the entire expression, as you see at the bottom of this rectangle, by 100 plus the coupon, a formula we can now easily program into Excel. Worksheet bootstrapping, which you now see in front of you, begins with the classical yield curve in column C, often referred to as the par curve, meaning the curve consisting of the bills, notes, and bonds actually outstanding in the market for this issuer. Note that we need to specify for these outstanding instruments their maturity, coupon, if any, with all of these notes having a coupon except the first one, which, as the bubble specifies, does not actually carry a coupon but earns a yield strictly from the fact that it's a discount instrument. And finally, we need to specify the price in this column D at which these bonds currently trade. Of course, you may be aware that the financial papers often combine all this information into a single yield to maturity measure for each tenor. But for our purposes, it is necessary to proceed as we are doing. If you need a refresher on what yield to maturity means, please review our module on bond fundamentals. As you can see, this par curve begins with the three instruments that we saw previously, and where we have inserted the yield of the first instrument, deriving it simply from converting a 95% investment amount into par 1 year later of 100, and therefore extracting from this data a very simple yield from this formula 1 over E8 minus 1 equal to 5.26%. You will therefore notice that this curve is upward sloping, but gradually does so at a decelerating rate, as is rather typical of many curves in many circumstances. We will discuss a little later and in more advanced modules in more detail why a curve that begins by being upward sloping must flatten quite a bit at longer maturities, indeed must more or less flatten completely at very long maturities, or quite often must even begin to invert. Again, we emphasize the yellow bubble at the top of the worksheet here points out to you that while the entry in column D for all notes starting on row 9 and below reveals that they are trading at par, and while all entries in column C starting in row 9 and below reveals the coupon of these notes, for that single instrument on row 8 whose maturity is 1 year, no coupon is paid, and all returns to the investor are earned simply by purchasing this instrument at a discount to par of 95 in this case, and redeeming it at par. And we remind you once again, finally, that we derived this yield from the algebraic equation that has just appeared in front of you, programmed into cell C8. Below this first row, and in particular in cell E9, we have simply inserted the formula that allows us to derive the 2-year discount factor from the cash flows of the 2-year note, exactly as shown previously in the slides. And then to the right of this column, we calculate in column F the cumulative sum of all DFs that have been calculated so far, including the one we have just calculated on this row, since you will recall we will need such a sum as we proceed to successive DFs. To illustrate, when calculating DF5 in this cell E12, for example, the formula you see here requires as inputs not only the 5-year notes coupon, which appears through the cross-reference to cell C12, price, the cross-reference to D12, and face value, the number 100 appearing
elsewhere in the formula, but requires also the sum of the DFs for years 1, 2, 3, and 4, hence the cross-reference to cell F11 in Lilac. The last item of note in the worksheet is column G, which simply reflects the formula we visited earlier for converting any discount factor into the zero coupon rate corresponding to that maturity, in essence by decomposing the discount factor over the number of years it covers. Comparing now in particular columns C and G with the par curve and the zero coupon curve, we see that for each maturity past 1 year, the zero coupon rate is slightly higher than the par rate. Beyond this general observation, it is difficult to generalize. While at first sight it may seem that the gap between these two columns increases as we go further out along the curve, as certainly appears so far to be the case in rows 9, 10, and 11 that we just highlighted, closer observation reveals that this gap continues to increase until row 13, describing year 6, peaking in that year at 48 basis points, and then actually begins to decrease a little, so that by the time we reach year 10, this gap has declined to only 40 basis points. Curiosity naturally leads us to ask whether these last couple of phenomena are constant, or whether they hold only when the par curve is upward sloping. To address this question, we turn to worksheet flat, appearing now, in which the par curve is now assumed to be flat at 5.26% instead of sloping upward as before. You see immediately that the par curve and the zero coupon curve now lie exactly at the same level, a reality you should be able to justify easily if you revisit the basic mathematics we examined at the beginning. By now your instinct is probably suggesting to you that if the par curve is inverted, we might find the zero coupon curve this time lying underneath it. And indeed, this worksheet labeled inverted confirms this very precisely and reveals, at least for the very smooth inverted par curve that we have programmed in this column C, not only that the corresponding zero curve lies underneath it, but that the gap between the two curves expands the further out along the curve we go.
The last thing we need to do before concluding this chapter on bootstrapping is to consider the more realistic case involving securities shorter than 1 year and coupons on notes and bonds that are paid more frequently than annually. We therefore suppose that in your market the government issues only 3-month and 6-month T-bills as discount securities, and also 1-year notes that pay coupons quarterly and are issued quarterly as well. Let us suppose that the notes currently outstanding in the market have the following terms as of June 30, 2009. Note, as expected, 3- and 6-month bills with a face value of 100, but in the rightmost column, a price below 100 and no coupon. So discount securities providing all of their yield in the form of this discount. But then, a 1-year note issued March 30, 2009, maturing March 30, 2010, and paying 9% quarterly, and then again, a 1-year note issued June 30, 2009, maturing June 30, 2010, but with an 8% quarterly coupon, so reflecting presumably some decline in rates that happened over those 3 months. Note in particular that since the 1-year note is issued quarterly, the instrument in the third row that was issued in March 2009 now has only 9 months left until maturity, and therefore only 3 coupons remaining. For this note, we can write the normal relationship between its price of 100.8 and its cash flows, representing coupons quarterly of $2.25 each, discounted appropriately by the right discount factor. You have probably guessed that DF 0.25 is the discount factor for a cash flow occurring 1/4 of a year from the measurement date, and so on for the other discount factors. But we know from the 2 short-term discount securities that DF 1/4 is 0.98 and DF 1/2 is 0.96, which enable us to write what has just appeared here. So DF 0.75 equals 0.9431. And this in turn leads to the 1-year note issued on June 30, 2009 and maturing on June 30, 2010, which appears in the bottom row. And for this 1-year note, we can write its price, 100.1, equals its coupons of $2, not $2.25, because that note had an 8% quarterly paid coupon. Each coupon here being again adjusted by its discount factor, and the final term in this rectangle being the coupon and the principal. And this finally leads to DF1 equals this expression here, which equals 0.9250. This completes this chapter 1 on bootstrapping techniques, on discount factors, and on zero coupon rates.